needs an introduction here. Obviously, without Richard, we would not have this workshop. He is really crystallography. And what I'm many generations below Richard, and I'm really still looking up to him. And it's really amazing what he accomplished. It was the first time that actually anybody has visualized a membrane protein structure by electron crystallography. The first time anybody has seen a transmembrane helix is actually based on Richard's work. And he also obviously got the first atomic structure of material dopsin, the first structure determined by electron crystallography. And so it's really, his accomplishments are endless. And he's also been the director of the MRC for a long time. And he has always promoted long-term visions, and that's really something I always admire about him. Things that have taken many decades to really pay off, he has always supported it. And I think I really admire his vision. He's always been at the forefront of thinking. So he has developed electron crystallography, and then he has also started to think about single particle electron microscopy, and that's what he's going to talk about today. And as you mentioned already this morning, there's always this problem whether single particle reconstruction is correct or not. It has always bothered me, because I never knew that the structure we determine is correct or not. And so this is for the first time that Richard had actually found a way to kind of validate whether the structure is correct or not. And Richard also has been one of the first to actually realize that detectors are going to be a major improvement in how we can boost the resolution. And although it's not in this talk, I hope in the end we can convince him to talk a little bit more about detectors, because I think it's really an important topic in our field. So it's a great pleasure and a great honor to give the talk to Richard.
Thomas, thank you very much. Anyway, no, it's great fun to be here actually. And I thought originally the request from Henning or Thomas was to do two talks, both about 2D crystals. And I thought, okay, I can manage that. But then things were changed to be one talk about 2D crystals and one about science. And of course, with science, you can talk about anything. Particularly as you get older, there are lots of things you've been interested in the past and still keep up with. So in principle, you could give lots of different talks about different things. But some of them require more work keeping up with the field, and others you have to refresh your memory and so on. And it's always, I think, better and more interesting if people give talks about something they're interested in now, because then they're naturally doing it. And also, of course, it's a little bit less work if you do that. So anyway, the thing that I've been interested in for a while, so our argument was that X-ray crystallography works quite well, but you have to make a crystal beforehand. 2D crystals by electron crystallography, as in this course, also works quite well. No doubt can be made to work better, but again, you do have to make the crystals. What do you do if your crystals don't happen or if they're disordered? And the great thing about electron microscopy, I thought, was that you do take images, so you get images of your particles. So you've got the amplitudes and phases of the image. So really, the true power of electron microscopy comes from the fact that you get the phases, which you don't do by X-ray crystallography. And so in looking ahead and taking a sort of overview as to how things will develop in the future, in electron microscopy or electron cryomicroscopy particularly, where you're looking at the atoms that make up the molecules. So my view is that the 2D crystals, that will continue to develop and will be a stable and valuable part of the future. But single particle electron microscopy and tomography, which are sort of open-ended, I think they will develop much more. The methods will improve and a lot more people will be doing it. So that is a real growth area for the future. And similarly with the helical arrangements, that will continue to be valuable, but of course you have to make your helices to start with. So about 10 or 15 years ago, we thought we ought to make more of an effort at LMB at Cambridge, and that was when Nico Grigoriev was there as a postdoc working on 2D crystals initially. We thought we ought to make an effort to look forward at very high, the possibilities of doing very high resolution with single particle EM. And Nico wrote Freeline and developed lots of collaborations, and he's continuing to do really well in that. And obviously we've continued. So it wasn't until a year or two later we started to wonder about how do you know whether you're getting things right? And as I sort of mentioned this morning, the great thing about crystals is you have spots. And in between the spots you have all this background. And actually that's what makes X-ray crystallography so good as well. You measure the spot, you measure the background, and you know you've got data. And you know you must be able to solve it. In X-ray, you have to get the phases. But in EM, as soon as you have the spots, particularly for the images, you've got the phases already. So even before you start, you know it's going to work. And you know that the answer you get will be telling you something that's true. The only thing about single particles, they don't have spots, and there's nothing in between the Fourier components. It's continuum. So how do you know what's noise and how do you know what's continuous? And the thing that doesn't exactly haunt me, but one of the things that's been most amusing over the 20 or 30 years is when people think they've got it right, but actually later work shows that it's wrong. And somehow or other, I remember more clearly all those papers that the X-ray crystallographers have published that turned out to be wrong than most of the other papers in X-ray crystallography. So we all know that the work on Rubisco from David Eisenberg's lab at UCLA, when they traced the chain and they got the small subunit and the large subunit, but in one of them they traced the entire chain correctly, but from the N terminus to the C terminus instead of the other way around. And that was, they had a meeting on errors in protein crystallography, and one of the sessions involved confessions from people who'd got it completely wrong. And then there are structures that were published as entirely beta sheet that turned out to be entirely alpha helix. I won't mention that, it was a worse error. So in the EM area, fortunately, we've been relatively free of this. Most of the helical stuff in the 2D crystals, you've got layer lines, you've got spots, it's sort of self-checking. But I think the single particle EM is a kind of dangerous area. Because what often people do is you take pictures, you get all these single particles, you can see them, you click on them, and they're very good and very powerful, and Spider and Imagic, the multivariate statistics for pulling out below the noise level images. And you then say, oh, I like these ones. You put them together, you do angular recall, you get a 3D model, and then you go around, you cycle it round until you have a self-consistent, relatively blobby density map. And you say, I've done it, and you say, well, how do I know it's right? And you don't really, until you get perhaps to a resolution where you can see alpha helices, or you can see beta sheets, or you can see side chains. And then that's how the X-ray people knew they were right. Although even with that, sometimes they got polypeptide chain wrong and so on. So this is what we've been wondering about. And actually, I have to find the computer. And so in about 2002 or 2003, Peter Rosenthal and I, so basically the talk's going to be centered on this work that Peter and I did, which was done actually originally. The idea was we would set up a very simple little piece of scripting software to find out what the absolute hand of our structure was. That was the original idea, by taking tilt pairs. And people had done this in the past with helices, with icosahedra. You take a tilt pair, Tim Baker had a nice paper about it, and you know the tilt angle, and you compare your 3D map that you eventually get. You compare it, having aligned it for the untilted map, you compare it, having tilting it by a positive angle and a negative angle with your experimental micrograph taken at a tilt. And it always agrees better with one than with the other, maybe only due to the noise, and you say, I've determined the absolute hand. So, but we thought we would do it a little bit better than that. And as we went through the work, we found out that what we had believed was a data set consisting of beautifully aligned particle images really wasn't like that. Some of the particles were properly aligned, but most of them were complete rubbish. But if we hadn't done this test, we'd have been quite happy with our 12 angstrom resolution map. So icosahedral. We'd done what everybody else did, except we did this other test on top of it. And then once we fixed things, it was very much better than it had been before that. So anyway, we published this paper, and we discovered that in addition to the idea of finding the hand, we'd been forced to think about other things. So there's about 5 or 6 points that are in this this paper. So one of them was finding the absolute hand. Another one was we'd been concerned, but how do we relate what we do in electron cryomicroscopy with what the X-ray people have been doing for years with protein crystallography? They have a different method of measuring how accurately their phases are. So they have figure of merit, and they say when the phase error is 60 degrees, the figure of merit is 1/2, and we're really pleased. In fact, solved structures have figures of merit of 0.1 or 0.2 at the highest resolution. So we wanted to do that, and when we got to the bottom of thinking about it, and the actual equations were worked out with Tony Crowther, we discovered that a figure of merit of 1/2, which is a fantastically accurate X-ray map, is equivalent to having a Fourier shell correlation of 0.14. And so we put this into a little appendix. And so one of the points in that paper is absolute hand. Another one is if you've done your merging properly and you haven't over-refined the noise, then this is a perfectly good Fourier shell correlation. And then we were also very interested in why is it that in the images, as you go to higher and higher resolution, all the diffraction spots fade out, often by an equivalent of a B factor of hundreds, whereas the X-ray people, they have 30 and 40 and so on. So by the time you get to 3 or 4 angstroms, your diffraction amplitudes are hundreds of times weaker than they would have been if they weren't fading out. So we said, okay, the reason EM maps look so beautiful and smooth and noiseless, whereas all the X-ray maps look noisy with little features here and there and so on, is because they haven't got any fading, whereas we've only basically got low resolution Fourier components. So you should sharpen them. And the reason people didn't sharpen them before is that they sharpen the noise and you get all these noisy maps. So one of the things in this was you should find out what your B factor is and use that to sharpen the map so you can interpret it in terms of the structure. But you must avoid sharpening the noise. So this same theory that was used to find out, roughly when can you believe it, you can use it to do the equivalent of figure of merit weighting, which is caught on as a name for weighting down the noise. And if you do both of these things, you get a nice map that you can interpret. And Jose, Jesus, and a lot of the things in this paper were a little bit clunky, and we didn't really polish them up to make them easy for people to use. Jose Fernandez, who was at Almira and is now in Madrid, he noticed this and he sort of, let's say, polished it up. And there's now a sort of web site that he created where you could download his version of this sharpening. And you give it the Fourier shell correlation and you give it the structure, and then it finds out what the B factor is and so on. It tells you what it is and it gives you the nicely sharpened map. So that's been kind of made user-friendly. And then the final thing, which we were most pleased about, is that if this works and you use your tilt pairs and you plot the parameter evaluation in terms of these tilt angles, and it works, then you know that you've got all your orientations right, and it more or less proves that your reconstruction is correct, because it's consistent with a tilted set of data that's sufficiently far away in angle that it couldn't do it by some type of coincidence and noise. So it's a lot of data that you're testing. So in the end, we've called it tilt pair validation, and it's of the orientation angles. But so anyway, so the main thing I'm going to talk about tonight is that we published this paper and we thought that's enough. You publish your paper, people read it, and then they do what it suggests if it's useful. But this is an optimistic view of humanity. So what actually happened is they read the paper and they say, we like this because it allows me to complain without doing a single thing other than reading this number. We can claim our resolution is higher. And out of 112 people who have cited this paper, 95 have cited it because they like the resolution. And actually the funny thing is, even when they say they've used a Fourier shell correlation of 0.5 because they don't believe the 0.14, they still cite the paper. And then there are people in between who've plucked a number out of thin air, like they decided to use 0.3. They cite the paper. So, we're pleased, but slightly disappointed. And then quite a lot of people have done this sharpening now, but, and I'll show it in a little while, not many people have done this. So what we've decided to do now is do quite a few things, a few different structures, and apply this, and then collect together a gallery of the results to give people a feeling for what they should expect if they do this. And where...
Can you warn us who should leave the room?
Nobody here.
Okay.
They will be named, though, but I won't. I won't. And then one last thing we also said, and I'll just show you one slide about this, is that we realized when we're looking at these resolution-dependent Fourier structure factors and the noise level, that if you only have one particle and you're not going to do any averaging, which is what you have in tomography, then you could never get a resolution very high. You could never get it much beyond 20 angstroms. And actually at the moment it's like 40 angstroms, unless you do subtomogram averaging, when in principle it's the same as doing the single particle averaging. So there's about half a dozen points in this paper that, we were pleased to have them all roll into the single paper, but it's this one here that I thought I'd talk about. Okay, so before we, so not everybody will have read this paper, I have to say. So I thought I should just give you an overview about what it says in it before showing you some of the results of this. So one of the things that it says, it has this, it presents a way of thinking about what we're doing with different structures by electron cryo microscopy that I think provides a useful framework for thinking about it. And this plot it's just made up actually, but it's meant to represent more or less any structure that you're looking at of a certain size. It could be smaller or bigger and so on. And the idea is we've plotted along the vertical axis the logarithm of the mean structure factor of as you go out and here's the resolution squared. And the idea is that at very low resolution, let's say you've got a 300 angstrom diameter particle. So at a resolution of 1,000 angstroms, basically all the atoms of that structure are at one point. And the structure factor at zero spatial frequency is just all the atoms, all the electron density involved. But of course, usually, and this was focused on embedded in ice, the protein is about 1.4 times the density of ice. So this zero scattering factor is basically it's 0.4 over 1.4, so it's 0.28 times the number of atoms. So that's the structure factor at the origin. And then it gradually fades out according to the radius of gyration of the structure. This is the Guinier plot, 1 over. And you get a certain slope depending on the size of the structure. And then it goes down until eventually the atoms, as far as the Fourier components are concerned, can be considered to be random atoms. And this is the X-ray crystallography scattering theory that Arthur Wilson invented about 1949. So Wilson statistics tells you that at high resolution, and in practice for proteins that means beyond 10 angstroms, the structure factors are roughly speaking all the same, and they're equal to the square root of the number of atoms. They add up naturally. So here we have square root of number of atoms. Structure factors are all the same on average. Of course there are weak ones and strong ones, because each individual structure is individual. And also, there is a certain form factor. The atoms have a certain diameter, and that fades, and it's slightly different for X-ray and for EM. So that red curve is meant to be the overall. So you start with 0.28 times the number of atoms, it fades a bit, and then it becomes almost constant, fading slightly. And in here, you have the region which depends on the shape of the molecule. If it's got holes in it, it'll have certain structures. If it's rod-shaped, it'll have a certain... So this is the shape solvent region between, shall we say, 100 angstroms and 10 angstroms. Okay, so that red curve is the number. And it's scaled in that way. We then take images of it in the electron microscope, and those images are not perfect. You have some radiation damage, you get charging, things move around, and it's blurred. And that blurring might have a different shape function. But to a first approximation, let's say it's a Gaussian, just like a temperature factor. So a Gaussian in real space becomes a straight line when plotted as a log structure factor against resolution. So that straight line is meant to be the fading of the structure factors due to blurring of the image. And in practice, that could be temperature factors if it doesn't move, 0, or it might be 100, or in some cases 500 and so on, depending on how well you've stopped your structure from moving. If it's not biological and it's gold atoms on a carbon surface, it won't be moving at all. And then we do our computing. We click on all the particles, we do all the alignments, and somehow or other we don't get the position very accurately or the orientation very accurately, so you have another blurring factor from the fact that you haven't processed it very well. We've called that B image. So if you add them together, you get it fading like this. Okay, so that's the 3 red curves. Then there's the noise level in the image. We're allowed to give it a dose of 5 or 10 electrons per square angstrom. You get a certain noise level from the electron statistics, and that, it turns out, we've drawn it roughly according to, that's the noise level there. Given to, in one image, you have that noise level. As you then take more images, a bigger crystal, more single particles and so on, you start averaging them. So for every 10 particles you average, the structure is the same, but the noise level drops according to root 10. And so that's being scaled down here. So 10, 100, 1,000. And when you work it out, and we have this theory that supposedly is, we hope it's right, turns out when you've gone to about 1,000 or a few thousand particles, depending on what, exactly how you define your noise level, your noise level drops below that expected for your pristine image of your structure. And in principle then, once you've averaged a few thousand particles, your noise level is below that of the average structure factor, and you've determined your structure. But if your image is blurred or your computing isn't very good, you have to make up for that by having more and more particles. And this is 100,000 million. And of course the noise level is here and it's fading at this level. So when the average structure factor goes below the noise level, that defines what your resolution is. And whether you take 0.14 or 0.5 for your shell correction, that's not a big difference. So that's the overview, and we think it's a useful thing because what it says is that for tomography, where you only have one structure, and you look at it, this is the noise level, and it intersects not at 10 angstroms, but well below it, and of course this is d squared, and that turns out to be 15, 20, 25 angstroms. Not a lot different from what you actually get in practice. So once we've got better detectors, the tomograms should go to 15 or 20 angstroms, because they're not limited by blurring and so on. And then it also tells you how many particles to expect. So this is the sort of the overview of it. We then applied it to this was our test. This was pyruvate dehydrogenase, which Richard Perham's group in Cambridge had been working on for years, and he gave us some of this specimen. We weren't particularly interested in it, but it gives nice pictures, and we've circled a 3-fold axis view, a 5-fold axis view. Actually, there's 10 things around it. And then this 2-fold, which is different from the 3-fold in that there's a little line across the middle, and then there's a big white blob above and below, and a little white blob to the left. So that's kind of what defines it. Anyway, you click on these, and you can use, we used a magic to make this structure, and then Nico's program, using this as the model, and these individual particle images to refine it to get this one. And it turns out this is about 8 or 9 angstroms or something like that. And then we looked back to see how does the real data compare to this theoretical thing. So then we have, this is the real data from that structure. So here it is, 0.28 times around. It's got this bit of noise in it. It fades, and actually you can't really see a straight bit. It's all just curving. But if you then look at this, the signal-to-noise ratio, which you can get from the Fourier shell correlation, if you then multiply, so I'm going a bit too quickly here. So you see some fade out. We've drawn the dotted line in here, which is a linear line in a log f over d squared plot. So that is a B factor of about, in our case, about 1,000. So quite a big B factor. How do we know that that was the line? Well, you can relate this figure of merit here. This is the X-ray equivalent to the figure of merit. See, this is the cross-correlation against a perfect reference structure which you imagine exists. And that's related to the Fourier shell correlation that we've all been plotting as 2 times the Fourier shell correlation over 1 plus the Fourier shell correlation to the power of a half. So when FSC is 1, this is also 1. But when FSC is 0.5, when CREF is 0.5, FSC is 0.14 if you work out that formula. So you can use this figure of merit weighting factor, which tells you the amount of your signal that's from your structure and the amount of the signal that's from noise. Figure of merit, that's what it's, figure of merit of 0.14 means that 14% is signal and 86% is noise and so on. So we multiply this factor by that red curve and you get the red line then. So you basically, this is noise at high resolution, and you can remove it by putting in the correct factor. And then you get this nice straight line, which gives you the B factor. And this is telling you how the underlying real structure in that image that we just saw is fading out like this, and at high resolution, say beyond about 10 angstroms or so, it's gradually being replaced by noise. And of course you could decide where you think it. There's still data out at 4 angstroms, but it's very weak. And so then what we do is we sharpen it by that B factor and dampen it by that damping factor, and you get that that dotted red line there, which is our best guess at the entirely experimentally derived EM structure for that protein molecule. Fortunately, there was another X-ray structure published of a different symmetry, but it was a homologous structure. And Peter took that, didn't change the coordinates at all, but rotated it just with 3 orientations and a translation into an apocedral structure. And that blue line is then the equivalent Fourier transform average for that completely model structure. We'll see that in a little while, and it agrees quite well. So that's the structure that we were working on, and that's the intellectual sort of framework that we've... So here is this CREF figure of merit now that we've defined, and that's... So here is the traditional Fourier shell correlation curve, and this would be 0.5 cross-correlation coefficient with a resolution of 11 angstroms in that structure. If you take this formula, converting it into a figure of merit, that's just directly compared. That curve is the one that results. You can see the negative is in the same place and so on. And so then a figure of merit of a half, 60-degree phase error, corresponds to this 0.14. And then when you do the cross-correlation between the EM map and the X-ray structure, you get that dotted line. It's not scaled very well at low resolution, but you get a half. And these atoms in the X-ray structure haven't been moved at all, except as a rigid body rotation. There's no bending or fiddling to make it look better. And so we think that proves that this way of sharpening and treating your structure is experimentally shown to be right. Okay, so now we come to this 9 out of 112. So most of these citations, up to Monday or something, are to do with my resolution is a bit better than I thought it was. But there were these 9 where they've used this tilt pair validation. And actually it turns out that disappointingly, most of them are ourselves or people who were in Cambridge. So for example, this was the one we published. Kyung-hee Lee did it, John Rubinstein did it, Tony Crowther did it, and then later on, John Rubinstein did it for yeast ATPase and V-type ATPase. And the only 3 not from our lab are, I have to see now, so hepatitis B surface antigen, which is from Oxford, Helen Sable's one of the chaperonins, and this DNA-dependent protein kinase from Phoebe Stewart. And the one that we like, and I won't say anything else about the other 2, is Phoebe Stewart's one. We think that's a 7 angstrom structure of half a megadalton protein only, and I'll show it a little bit later on. And she must have sent an awful lot of emails to Peter and I, and got it to work really well. And go on, sorry.
Is there any way that you're actually going to provide a nice script that we...
Yes, that's coming also. We got that because Peter and his student Sebastian have now got it on their website. And so Fernandez has got the sharpening and figure of merit weighting on his website as a lovely little script. And Peter and Sebastian have now got the tilt pair thing on the site. And I have now also there are two ways of doing it. We had a program that was a little bit clunky. That's all been really nicely cleaned up and sent off to various people who are using it. But I'm going to show you some of the results with both of those. So we're trying to make it, we're trying to show, let's say, a panel of results that give you a feeling for why it's a good thing to do, and also send out various easy-to-use versions of the programs as opposed to the ones that we had in 2000, which were a bit clunky. Okay, so that's the same structure I showed you, the same Fourier shell correlation, and contoured at a different level. You can see it's actually mainly helices, and it's quite a nice structure. So here are the tilt pit. This is one micrograph. And 50 particles have been picked on. Peter did this. So 50 particles have been picked on it, and then you tilt it by 10 degrees, and you take another micrograph, and you pick the same 50 particles. So you have two stacks, and you can look at them. And I believe if you look at particle number 6 on the second picture, you can see that's a twofold view, because you've got the big one and the two big ones and the two little blobs and the little line in the middle. And if you look up here, it's more like a threefold. And roughly speaking, I can't remember the distance between twofold and threefold in icosahedron. Someone will know, but it's not a lot, 10 or 15 degrees. So you've gone mostly from a threefold to mostly a twofold. And here, number 49 is the same. So here's a twofold, two big blobs and two not quite so clear little blobs, and then again that's a threefold. So you can actually almost find the orientation by eye. And this particle is 1.5 megadaltons, so it's not very big, but it's not very small either. And you can see if you get it smaller, it'll be noisier, but hopefully if it's bigger, they'll be clear. Anyway, that was the one that Peter was working on, and this is the published map. So so what you do, this is the procedure. You take all those 50 particle images, and you take that 3D model, and you run FreeAlign once, which takes maybe an hour or something like that. And you get out there, you get the orientations of all those 50 particles, and then you say, I want to test whether the model, the 3D model, and all those particle images and the orientations you get are correct. So what you do is you use these orientations, and then you pretend that you know the tilt axis and tilt angle, but you explore it, say plus or minus 30 degrees in both directions. So we're restricting it to having the tilt axis in the plane of the micrograph. So we're assuming that when you tilt it, the beam is perpendicular to the goniometer, which otherwise, if you don't assume that, you allow more degrees of freedom, and it won't work so easily and so nicely. So then you get, and the way Peter did it, he did plus 30 to minus 30 in something like 2 degree steps in two directions. So there was 1,000 parameters that were written out, and you then run FreeAlign again in an evaluation mode where you get the phase residual for the average of those in the different orientations. And if you've got the correct model and the correct orientations, you should get a minimum at the angle that you set on the goniometer, which the data doesn't know and the program doesn't know, and in the direction of the tilt axis. And here, this would be if the two images were the same. So here you have the minimum, it's exactly at 10 degrees and exactly in the direction of the tilt axis. And I have to say, when we first ran it, we didn't get this result. We had run FreeAlign, we got the orientations, we were happy with the structure. If we were normal, we would just, say, we finished the project. We got a minimum at about 1 or 2 degrees. It was basically bad orientations. Most of the particles were rubbish. It was in the right direction, so we would have determined the absolute hand. But by making sure we had used the optimum resolution, we had various weighting factors, got the defocus right of all of different parts, we eventually got it. And so the difference between the correct hand and, let's say, the equal direction in the other 60 degrees, it's a 17 degree, and Peter called this the freehand difference. But actually it's a minimum in a plot of the tilt pair tilt pair parameter plot, phase residual, averaged over all the particles. And the fact you've got a minimum there doesn't prove that the orientations of all your particles are correct. It doesn't even prove that the orientations of half of them are correct. It just says that on average you've got a minimum. Some of them might be rubbish. But it shows that it's not entirely, your structure is not entirely rubbish, but it doesn't prove that it's entirely good either. So we had another program which is called tilt diff, and what that does, it takes the same data that you got here and here, but you run free align once, as you were doing to get that plot, and a second time, assuming these are completely independent particles. You get new orientations out, and you can refine it as much as you want till you get your best orientations. And then you read in the 2 parameter files. So this program is a very small program, and it doesn't need any images. You just give it 2 sets of 50 particles, Eulerian angles. And then it works out what is the tilt axis and tilt angle that can make one particle morph into the other and does all the symmetry and so on. And when we first did it again, it was kind of a bit of a random. It turns out it was roughly right, but after we'd got all our angles optimized and all the weighting and the resolution and defocus and so on, we got quite a nice cluster in exactly the same place as we got in that other plot. A few of them are not very good. They might be because the second particle image, the second image is rather damaged. It has about a 5-degree higher residual against the 3D model. So definitely the first images are better than the second. But it gives you a nice cluster, and that's where we stopped. We said, okay, we published something. Now what we thought is, we need to make this easier for people to use, and also give a feeling for how well it will work on bigger particles and on smaller particles. And so we then, so I rewrote this program recently, and this is somehow that comes out in a different orientation as well. But anyway, it's the same. It's exactly the same parameter file. So if you look, there are 4 over here, there are 4 over here, and so on. And it shows the same minimum. It's got a 2 or 3 degrees. So it basically tells you that the orientation you get from one particle in one image might be correct, but you do it again from a different viewpoint, you get a difference of 2 or 3 degrees. So probably it means the error in your orientation angle is 2 or 3 degrees. Might be a bit better on the first image and a bit worse on the second image, and that limits you, for 200 angstrom diameter particle, a 2-degree phase error is moving the edge of the particle 5 or 6 angstroms, something like that. So you wouldn't expect to get very high resolution, because that's not a very good orientation. And that may be true of all the smaller particles. So then we went on, and this is just a few more examples. So this is the chicken anemia virus that Tony Crowther worked on, same time, and this is his field of view. So he picked a few particles. It's a rather nice picture with these flower-shaped things. And it was an 11 angstrom structure. Actually, it's about the same as the pyruvate dehydrogen, because that was the he was still sticking to this conservative 0.5 Fourie-Shell correlation. And this was his plot. Again, it was a 10-degree tilt. That was the untilted one. Here it is. It's not quite at 10 degrees, it's sort of at 9. And the difference is about 13 degrees in the phase residual from one side to the other. And they also did, although they didn't publish it, so that these were his 45 particles, and you can see some of them have large pieces of dirt or contamination right next to the particle. So maybe those ones won't have such good orientations. And when you look at the individual particles then, you get a tighter cluster, so 1.5 or 2 degrees, something like that, but you still have these outliers, and the ones that have the star means that it was consistent with having the tilt axis in the plane. These ones with pluses, which are a lot of the outliers, means you can't really believe them because the tilt axis isn't, the residual isn't, it's not very, the angles that you get in the 2 micrographs aren't really consistent with the tilt axis being in the plane. So, and this is a 3 megadalton particle. So what we're saying now is we have 2 examples, a 2 or 3 degree orientation uncertainty with a 1.5 megadalton particle, and then a bit less on a 3 megadalton particle. So what, go on, yeah.
Shouldn't the width of this plot be, I mean there's a square root of 2 in there, so it's actually more precise by a factor of the square root of 2, because if one of the two tilt
Yeah.
cells is off, then
Random.
the other one might still be okay.
Yeah. The first one might be okay. So actually this is 10 degrees, you see. So if you take it from the average, they're probably up to 4 or 5 degrees. So the average is probably 2 or 3 degrees. So root 2 would be 1.5. And maybe the first, it might be 1 degree. But you know, we weren't emphasizing, we're just looking at it. Okay, so then one of the people who has had a nice map is Zhang and Grigoriev. They had this rotavirus about 2 years ago now. It's a 20 megadalton virus, so much bigger. And they had side chains that they could see, and they had a nice resolution. And when they did all their averaging, it was about 4 angstroms resolution, and so on. So it was a really nice map. They had a B factor of 450 that they applied to sharpen it to get the map. So we emailed Nico a few months ago, and his student, James Chen, kindly took 10 pictures on his slightly defective. Their detector had been sent back for repair, and they've been loaned this detector. And so it's not got really proper, you know, the 4 quadrants aren't quite right. But anyway, these are the 10 micrographs. So he sent 10 micrographs untilted, plus 10 accompanying micrographs that were tilted at various angles. And we'd said, you know, 10 degrees, but actually he did them at -10, -5, +5, and +10. So different ones at different angles. And so he then emailed us the 20 micrographs and a 3D model. And then we just put it into the same system. And this is the thing this is the plot that we got. So it's exactly the same plot as before. And we had to modify it slightly because since these particle images are all taken at different angles, it now plots a different color as it changes to a different particle. So let's say, you know, image N1001 and 1002 is that one there that's kind of pale brown. And all the particles on it, I can't remember, there's 4 or 5 of them, they're all rather nicely clustered, fairly near to 5 degrees, maybe 4.5 degrees. And then the next one, which is, sorry, I must have labelled these wrong. See, it says 3.83 and 4.5, might be the other way around. Anyway, 4.5 and 3.8, they're not 5, but they're close to it. And then here are the ones that were supposed to be plus 10 degrees, and there are 3 of them. And again, they're not, none of them are 10, they're sort of 8.6, 8.8, 9.3, and the scatter on each of these groups of particles that come from one image is now down to 0.1 or 0.2 degrees. And actually that's what Nico and Zhang estimated in their paper. They said, we think we've determined our orientations to 0.1 or 0.2 degrees. And the funny thing is, it didn't really seem to matter. It's such a beautifully big and well-determined virus. So you can look at these and you can see the pattern in them. So the orientations are really robust. And the fact that there are no outliers, what that shows is that the orientation on the first image, the low-dose image, is pretty good. But the orientation on the second image is also pretty good. So the scatter isn't very much. But you can see there's some of them. This was supposed to be 10, but actually he says he thinks he forgot to, the untilted one, he forgot to turn it back from the previous image or something. So it's actually a difference between plus 10 and minus 10. So therefore it's 20. But the clustering is quite good. But okay, so the thing we learned from this is that the orientations on these big particles, if you've got a resolution limitation, it's not the orientation that's the problem. The orientation comes out quite well, and it shows that basically all of them are right. And I think that's what they think now. They've got all their orientations right, and the reason it fades out in 4 angstroms rather than 3 is for other factors. You know, let's say it's convergent beam illumination, or beam tilt, or the particles are deformed, something like that. But the interesting thing for us, which was completely unexpected, so this is, if you like, a new thing, it would be nice if someone would continue it. These goniometer settings I mean, I think they're pretty accurate. They've got encoders on them, and the clustering is clear. So each of the images that you get, you take a picture and then you tilt it, and you take another picture, and all the particles seem to go with that particular part of the specimen. So our interpretation of the fact that this isn't exactly 5 or 10 degrees, and nor is it exactly along the same tilt axis, how can the goniometer possibly change its angle? It's accurate to, you know, 1,000th of a degree and so on. And yet here we've got an apparent tilt axis difference from the goniometer movement that's possibly 10 or 15 degree difference. So our interpretation is that it's the same as when you put the beam on it and your image is blurred. You put the beam on the specimen and you start taking your 1 second exposure, and during that 1 second exposure, as soon as the beam is on it, the particles and that bit of ice with the particles in it starts to move. And it may move in X and Y, it may move in Z, but it may also tilt slightly. And so you then integrate your image for the duration of that exposure, and what you get for the orientation is the average orientation as it was moving during that exposure. You then put the beam off and change the tilt angle by 5 or 10 degrees, exactly 5 or 10 degrees, and then you may refocus it in between. You then take another picture, you put the beam on it again, it continues to be damaged and continues to move. And so what you're getting is movements of 1 or 2 degrees in orientation during a normal exposure. And you know, there's no reason to think it's any different for smaller particles or larger particles, but it's the first time it's been noticed because it's such a nice big particle with such an accurate orientation, because the particles are so big and so well determined. And you know, I don't think James hasn't. We said it would be nice if he just took pictures without refocusing in between. He could take 2 pictures without bothering to change the tilt axis. Lots of things like that. It would be so. If anybody has a big particle that you think the orientation's you could do a separate little side project exploring how the orientation changes as you destroy it with the beam, and that would be very interesting because you need a theory as to what's happening to your specimen before you can fix it. And if you've got the wrong theory, you'll fix the wrong thing. So you know, it's quite important. Anyway, so that was the bigger particle. Okay, so then what about a smaller particle? So John Rubinstein's been working on lots of ATP synthases, and these are his 2 plots that were published. So the left-hand side is published quite recently, 2010, and this is a V-type, V1, V0, thermophilus ATP synthase. And it's a nice structure. It has the big F1 part, the little F0 part. It has 3 stalks and a collar. So it's got an envelope that gives it something that you can see when you look at the micrographs. And when you do this tilt pair validation, they use, because it's a smaller particle, they use the 30-degree tilt. So they get a nice minimum at 30 degrees. And the difference between the minus 30 and the plus 30 was a 15-degree phase. So it's very clear. It shows the structure is right, and you look at it, and I think it's about 17 or 18 angstroms. The one that he did when he was in Cambridge was a tricky. It's bovine F1FO. There's no collar. There's 1 stalk. It's very weak. He had to go to considerable trouble involving some subjectivity in deciding what the orientations were. But he did get a 3D model, and he did do tilt pairs, and he did get a minimum in the right place, 30 degrees also. But the difference there is about 8 or 9 degrees rather than 14 or 15. So this one's definitely weaker, but we thought, okay, it validates the structure. But what you don't know is how many of the images used in that tilt pair, how many of them were good and how many of them were bad. And similarly here, how many of them are good and bad. And remember, all of the big 20 megadalton viruses, 100% of them on the second image were perfect. Whereas on these icosahedral structures, 1.5 to 3 megadalton, you're up at about 90% of them are okay, and then maybe only the second image is bad. So anyway, and John had never run tilt diff, and so we've done this. So this is this Thermus aquaticus, which is really a lovely structure, nothing wrong with it, but it turns out this is 60 degrees is the maximum, so this is 60-40. This is the clustering along the axis again. So really only about half of them are orientations that agree between the first and second micrograph. Doesn't mean that only half of them on the first micrograph are right, but it's unlikely to be all of them. And this is this is kind of validated. Whereas on the bovine, much weaker, much harder, there might be a few. This should be here, but not really. So and this is about where we haven't run. We've only done. There's only 5 of these tilt diff plots being done so far, and so what it shows is that. Well, we'll come to that in a moment.
Again, there's again the fact of the square root of.
There's a square root of 2, yeah.
So 75 would be the first. 75%.
No, it's not the square root of the number. It's the square root of the deviation in the angle.
If 75% would be correct, you would have half of them show up in the right position.
Yeah.
So
these are both validated structures. These are both correct structures. But out there in the literature, there are lots of other structures that we think might or might not be correct. They're off on this side of the, and no one's tried it on those ones. So this is the one that we think is nice also. This is about the same. This is 500 kilodalton. This is Phoebe Stewart's work. And these are both from her paper, which is 2008 in structure. And her particle also, it's 500 kilodalton. It's got an awful lot of structure to it. It's got these wide gaps, so it's got a molecular envelope with some shape and so on. And this is her tilt pair parameter plot for the average of all her, and I don't know how many tilt particles there were, but she had 300,000 particles in this structure, and it looks reasonable to about 7 angstroms. And there's actually an X-ray structure now from Lynn Sabinda and Tom Blundell of the same DNA-dependent protein kinase from a different species, but it's been crystallized in 3D. And it's about the same resolution. And if you look at it, the features are similar, but it's obviously slightly different. But I think this is validated both from this and from comparison to X-ray. But here her difference is it's something like 3 degrees. So our anticipation is that a smaller proportion of those particles that were in that tilt pair will be contributing to that minimum, and some of them will not be. So Phoebe's promised she'll try that. Okay, so then we come to how do you do it if you want. So Peter and Sebastian just put this up on their website on the 22nd of July. So it's the same data that I showed you at the beginning, the pyruvate dehydrogenase, although they're doing it. So basically you send to the website your map and your the 2 stacks of images and the orientation parameters for the untilted one. And then it takes the orientation parameters, predicts them for plus or minus 20 degrees, and does the residual, averaged over all the particles, but it also plots the individual particle, where the minimum on the individual particles are. And they're not all there, some of them are off the edge of it. But it gives you a list of the particles below average and above average, and the ones that contribute to the minimum and don't. And actually, if this goes on for pages, each particle has its own average. And so all you need is a stack of untilted and a stack of particles and a 3D model, and the orientations that you believe to be the starting point for the untilted ones. You send that to the site, and I haven't quite tried it myself, but this comes back. And I think the next one is just a slightly bigger view of the same thing, so you can see. So they've managed to get it down. So we had 43 when we published. They've now got it down to 39. But out here it's 50. So actually it's not a lot different. The difference between the correct and the incorrect. So our conclusion was that this idea of doing tilt pair bandage, it works really well for big particles. It makes you feel much more confident and happy afterwards, because the orientation determination is very well done, and then coincidentally you learn something about what's happened to your specimen during your normal imaging. And we think it works quite well, 1 degree or 2 degrees, 3 degrees, for medium-sized particles, but the orientation is not perfect, and maybe the main limitation to resolution. But once you're below about 1 megadalton or half a megadalton, particularly if your particle doesn't have much structure to it in terms of its envelope profile, then it's much flakier. And so we need more work to explore, what it should look like. And actually, we haven't ourselves done a particle of that size yet. So that's one of our projects that we're trying to do at the moment. Okay, so there are a few other things so that was the main thing that we've decided to focus on at the moment. We're going to collect together maybe 4 or 5 other sets of tilt pairs and 3D structures, and then publish a sort of collage review so that people have all this in one place, and that if you have a new structure that's of a certain size, you can say, well, it's as good as, or better, or worse than what other people have found for structures of the same size. And then obviously if people want to try for things that are 100 kilodaltons or 200 kilodaltons, I think at the moment it's extremely unlikely to work. And whether that means that the structures are wrong, or only that you can't prove they're right, that's where you need to be developing new tools for the future. And I think that's very important for our field, so that it has a reputation for rigor and correctness rather than something else. All right, so I've got just a few other slides. So this is the same tilted micrograph I showed this morning in the 2D crystal things, where we've plotted image amplitudes against electron diffraction against resolution squared this time, showing you that it's apparently it gets better than you'd expect for simple blurring, but that the apparent amount of disorder at right angles to the tilt axis, and that could be because of vertical movements of the carbon and so on. It is a bit, or it could be just lack of flatness, making it more blurry, so you haven't unbent it so well in that direction. But the apparent fade out along the tilt axis, where it's essentially an untilted picture, is less than it is perpendicular. That's the 2 symbols there. So then, so what I wanted to say was, so what would be nice would be to understand where that fade out comes from. And I mentioned this morning that using thick carbon seems to be a pretty reliable cure for imaging of paraffin crystals. We haven't tried it on these ones, and nor on tilted pictures. But one thing we always thought was important, and I think some of you who've been at meetings before will have seen this next little slide or two that I'm going to show us. One thing is, you do have radiation damage, and radiation damage does cause high resolution Fourier components to be fading out and to be damaged before the low resolution Fourier components. So the question was, what is the contribution of radiation damage to this fade out with B factors of 150 or 230? And for comparison, Hongju's structure, which is a 3.3 angstrom icosahedral virus, they estimate their B factor is 240 for that. Nico estimated about 400 or 450. Our pyruvate dehydrogenase, we estimated about 1,000. And that's what sort of limits the resolution as well. But the question was, what is the contribution? And you can, from the published literature, you can work that out. So radiation damage in structural biology, X-ray people get around it by just averaging over lots of molecules. 2D crystals, you've got 10,000, and a million by the time you've got lots of crystals. Single particles only contain 1. So the radiation damage is one contribution to the resolution limitation, and that's what causes the noise level in all the maps and causes tomography to be limited to 20 to 40 angstroms. So the question is, what is the contribution of radiation damage in that blurring, and how much averaging do you need? How closely you can get it? And not many people will have seen this, but this is a paper by Kuyama, who's worked on rhodopsin and bacteriodopsin. It's an X-ray group. And what they did was to expose bacteriodopsin crystals to different doses. And you can convert doses from X-rays into doses for electrons in terms of the same amount of energy deposition. So it turns out 10 to the 16th X-ray photons, 13 to 15 keV per square millimeter, deposits the same amount of damage in each of the molecules as does 5 electrons per square angstrom, roughly, in the EM, give or take a factor of 2. So what they've done here is to apply to the this is crystals of bacteriodopsin that they're measuring the spectrum of, and that's the optical spectrum before they irradiated it, and then they do 40 seconds at 10 to the 12, so that's like 4 times 10 to the 13, and it begins to fade. So at something like 10 to the 14th, 2 times 10 to the 14th, you've killed half of the color of the crystal. So you've done something to it, not necessarily, it's still diffracting, but so it turns out that at a dose equivalent to 0.1 electron per square angstrom, we can't measure the OD on the grids, but it will be the same. Half of the OD will have been blasted by this dose. And that's the safe dose where you could say, you know, you're not really damaging it much. But actually, we're using 5, 10, or 20. We're up by factors of 100 over that. And if you do look at X-ray, these are different doses, up to 10 to the 16th, and you can see bits of the protein begin to fall off. So the aspartic acids fall off. So for example, in the original bacteriorhodopsin experimentally determined electron microscopy maps phased by imaging, the images are all taken at 5 or 10 electrons. So one of the reasons you don't see the aspartic acids is that the radiation damage has caused them to as they fall off and turn into CO2 or something like that. So you get real damage here. So this is just to say that the way we have to do electron cryo microscopy, we are actually doing quite a lot of damage. And there's no possibility, I don't think, of us doing anything at 0.1 electrons per square angstrom. The X-ray people can do that on big crystals, but increasingly they're using little crystals and they blast it just as much as us actually. So they have the same problem as the EM people. Okay, so this is the data on fading, and the main one is from Holger Stark's PhD with Fritz Zeppelin, and someone was asking me for that reference earlier. It's ultramicroscopy 1996. Nigel and I did it at room temperature on bacteriorhodopsin and catalase and bacteriorhodopsin, showing the fading of it. And the high resolution ones fade faster than the low resolution ones. And what Holger did is to group all the reflections and measure lots of them and do radiation damage, electrons per square angstrom, 100 kV I think it was. The 7 angstrom ones fade at this rate. The 3 angstrom ones fade at that rate on this log scale. So they're down to 1% after 3. But at liquid helium temperature, it's slower. So the 7 angstrom ones are similar, but the high resolution ones fade less. And then what you do when you take an image is you integrate the power as you kill it. And we go beyond this actually in the image, 10 or 20 electrons per angstrom. So basically you're destroying the specimen. And when you integrate the power in structure factor under that space, it turns out the slope more or less gives you the integrated power. So basically, you get 4 times the structure factor at low resolution than at high resolution compared to an undegraded electron diffraction liquid helium, and 7 times. And if you convert that just with the formula e to the minus b over 4d squared, then this relative fading and the fact that the images are taken at high dose means that it's sort of 70 to 90. So let's say 80, a B factor of 80 is what you would expect from radiation damage to biological specimens, purely from radiation damage. And so everything else ought to be able to be cured by preventing it to blur. So when you have a B factor of 250, perhaps 80 of that, a third of it, is unavoidable from the radiation damage. The rest of it, from blurring, imaging, whatever, computing, ought to be able to be cured. Many of you will have seen. Go on, sorry, Henning.
If you could go back once,
yeah.
Please. It's a log scale. So is it so that a 7 angstrom structure is almost or suffers very little from the temperature, nitrogen versus helium?
This is slightly steeper than that. So that would go down to about there, which is about 30. This one is about 60 or something like that. I mean, it's been proved that liquid helium causes the spots to fade 2 times less or something than the liquid nitrogen. And obviously at high resolution, it's also about 2. It's better. Liquid helium is better for electron diffraction. Doesn't mean it's necessarily better for imaging because there are other technical factors. But if it didn't move, it would be better for imaging by a factor of 2. But it was the ratio we were looking at in order to estimate this B factor, because you've killed it, and if you take another picture, there won't be anything more on it if you're up at 10 or 20 electrons per square angstrom. Okay, so I was just going to convert this. Many of you will have seen this is our model for calculating it. This is our table showing how many particles and what resolution that you get to. And this is our kind of universal resolution calculator showing how important B factor is for getting resolution. So this was the work of Peter Rosenthal with a B factor of 1,000, showing you that with 3,600 icosahedral particles, which is something like a few hundred thousand asymmetric units, in theory you get this, and in practice you get this. You get 8.7 angstrom resolution according to this 0.14 criteria. This is what you predict for structures of different B factor and fading, and the best you can do, we're saying now, is about 80. But what it means is if you fix everything and you have a B factor of 80 from a well-ordered structure, you would get to 4 angstroms with something like with a few thousand particles, and 3 angstroms with 20,000 particles or something like that. Not very many, and people are using it kind of several million at the moment. So these are Nico's 2 points. That's with icosahedral averaging. He reckoned he had a B factor of 450 or 500. And this is after his further 13-fold averaging from the T equals 13 structure. So this is rotavirus. And then Hong Chu had a B factor of 240, he reckoned. And I can't remember, but he had millions of particles. So it works out pretty much on there. So basically, what I'm saying is that there is an understanding of how well we're doing and why we're doing it. What we haven't got is a cure for it. So we have a diagnosis, but not a cure. It's like being told that you're going to die tomorrow from cancer. Tough shit, really. But actually here, there ought to be a solution if we keep at it. And so I think this is going to be the last slide. So the idea was that the contrast is being lost unavoidably from radiation damage. And this was the bit about detectors. So at the moment, we don't have very good DQEs at the moment. And it's poorer at high resolution and low resolution. So at the moment, the detectors are contributing part of this. And if you could have perfect detectors, which are entirely doable, technically, in principle, and obviously in practice, with the expenditure of considerable more resources in cash, you ought to be able to knock 60 off everything that you're doing. And then this is the thing that I think not many people are working on. Charging and mechanical movement is probably the biggest factor that's in principle curable, but we don't really have a way of doing it in ice. Although having very thick carbon for 2D crystals does seem to be a good way, if that's what your main limitation is. It may be that disorder of your crystals, let's say they just have they're not very well ordered crystals. And X-ray people that have B factors of 200, they say, oh, my crystal only goes to 10 angstroms. And they throw it away. They don't pursue it because they want it to go to chemistry and to atomic structures, 3.5 angstroms and so on. But maybe that in the EM, if you've got a 2D crystal, you could do some kind of limited single particle work, as people have been discussing and as Henning mentioned this morning, and overcome disorder between molecules in 2D crystals, and this would be a technical thing in the imaging. So there are a number of detectors, some of them are trying to prevent movement, particularly for single particles in ice, and then maybe some kind of 2D unbending. And I think, yeah, that was where I was going to stop. So they were all my, let's say, things that I feel I would like to grind axes about, and that we're really interested in at the moment. And we are going to be trying hard on these, let's say, there are not many really big, well-ordered structures. Icosahedral viruses are one. There are lots of lovely little protein structures, 10, 20, 30, 50 kilodaltons, that are being very well catered for by NMR and X-ray. But there's this region in the middle between about 100 kilodalton and the megadalton, where there are lots of very interesting complexes, some of them quite transient. And the two that we've focused on, which we would like to improve the methods to tackle, are human voltage-gated sodium channels. They're about 1/4 of a megadalton. And G-protein coupled receptors with the G-protein complex bound to them. They're about 200 or 300 kilodaltons. And in principle, these are two areas where at the moment, it doesn't look like anybody can find the structure. You know, they're very unstable. No one's made crystals of them. They're too small to do cryo-EM properly at the moment. So this is an area where technical improvements in the field might make it really open up. And then there are lots of other complexes, some of them transient and unstable. So I think it's got the field, our field, has got a great future. And keeping together the 2D crystals, the helices, the single particles, and tomography as under one umbrella will be quite productive. And I think we've heard some of the talks. Anyway, thank you very much. So we revert to the beers now.
No, not quite yet.
Not quite.
So thank you very much for another great talk, and I'm sure there are questions.
Richard, could you go into a little more detail that what improvement that you did to optimize, did some optimizations to make the original plot went from scatter to...
Yeah. All right, so it is described in the paper, which, you know, won't go away, but I can just summarize it briefly. So when we started, our philosophy was we didn't know the defocus, and we couldn't find what it was until we had got a 3D model of this icosahedral pyruvate dehydrogenase complex. So we decided that we would only use the data out to the first zero of the contrast transfer function, which was about 30 angstroms. And it was quite good to 30 angstroms. So we truncated it at 30 angstroms. We guessed the defocus, which was about 1 or 2 microns. And so we weren't worried about getting the defocus wrong and getting the wrong orientation. So we ran it repeatedly, got orientations by Imagic and by Freeline, and we got our model, and it was not a lot different when you looked at it at low resolution. It was about 13 or 14 angstrom resolution. And we said, oh well, that's how it is. And actually Hong Chu had been working on it when he was in Baylor before, and they got sort of similar resolutions. Okay, so then, what did we do? We then developed this tilt pair plot, and it looked dreadful. It really did look like you could determine the hand, but there was no minimum at 10 degrees. And the tilt diff thing, we thought maybe the bug in the program, they were all over the place. So, but then we continued, and we then said, okay, well, maybe we should put the data out to the second minimum, which was about 20 angstrom resolution. So we then spent more effort getting the defocus right, and then we went then to the second minimum, which is about 20 angstroms, redid it, and instead of the minimum being at 1 degree in the right direction, it still wasn't at 10 degrees, it moved to about 6.5 degrees. So it was better. So then we said, okay, what else can we optimize? So we then had a better 3D model. We then refined the defocus of this 1 micrograph, or 2 micrographs, till we were sure we got it right. No astigmatism, just defocus. And then we varied the resolution from about 25 angstroms to about 14 angstroms. And actually remember, there's data in it probably beyond 10 angstroms. But very weak data probably doesn't help you determine the orientation. So we varied the orientation, the resolution. We found that helped. So we optimized it to about 14 or 15 angstroms resolution. Then we introduced a weighting scheme. We said, well, are we putting the correct weight between the low resolution and the high resolution data. If you put the wrong weights, then you overemphasize one and you don't extract the data out of the other. It's a bit like using half the data instead of all of it. So that we then introduced an extra thing called B weight. And you could vary that. You could put it plus 10,000 or minus 10,000. You can sharpen or dampen the high resolution. And I think we found that, I can't remember which way around, but it was 3,000, a B factor of 3,000, which I think sharpened the high resolution terms a bit, but not too much, because it's, and we've got a plot of that in the paper. And this phase residual difference, it sort of, it goes up and up and up as you change the B factor, and then it comes down and down as you go too far. So getting the right balance improved it a bit as well. And then, I don't quite remember what, there were 2 or 3 other parameters. The number of cycles of refinement you do, the low resolution limit as well as the high resolution limit. And in the end, we got most of the particles, 45 out of 50, to agree, and then the minimum was right on the 10 degrees that we got. Then we stopped. We couldn't think of anything else to vary. So basically all the, and of course if you were using Spider and a Magic, it would have different things. So you always have a bandpass filter. So you've got the low resolution and you've got the high resolution. You've got the shape of it, you've got the resolution, you've got the defocus. There's lots of parameters that go into it. And if you just do it with the parameters you think will be correct, you'll get orientations, you'll get a structure. But you have no way of knowing whether you're improving it or not unless you have something extra to test. So in other words, in the 2D crystals, remember I said this morning, what we did to know whether we'd gone too far, we used the low resolution spots, say out to 6.5 angstroms, to do the unbending, and we then use the high resolution spots. We look at the signal to noise ratio because you can see it to know have we optimized the defocus, the size of the reference area, the number of cycles and so on. And if you do it wrong, if you make the reference area too small, usually you start with a big one and you keep making it smaller, picking up finer and finer variations. And all the time you see your peak at high resolution, which nobody is looking at except you, getting bigger and bigger. And then you go too far, it starts to come down. So you then back off and you've got it off. So we're doing the same. So we're trying to use tilt pair as a piece of data that was not involved in the structure creation as an evaluation for how good the structure is. And so as that gets better, you've got an external thing that you weren't looking at. You're not allowing it to look at. There could be other things you could do than tilt pair. For example, one thing that's been suggested is you've got your 300,000 particles, you divide them into 2 halves, and you process them all completely independently. You don't allow each one to look at the other. And it's preferable if you don't allow the person doing it to speak to the other person doing the other half. Because if it's you doing both of them, you'll say, oh, I like this class sum. I'll pick this one. And then you look on the other one and you say, oh, I like this one. And it's the same one you've picked, or a similar one. And then when you put it together into 3D to make your 3D model, angular reconstitution, you say, oh, I like these orientations. And so there's an element of making them agree with one another. So, but if you leave them separate, and preferably 2 different people do it, you can then say, well, how well do these 2 half structures agree? They haven't been refined against the same 3D model. They've been kept completely separate. So then, of course, you have to orient them. And that in itself, you have to pick the resolution that you do the orientation. If you orient right out to the edge, then all the noise in both of them will be being oriented. And the number of it's 50,000 orientations you're allowed to try. So you can even just taking 2 apparently separate structures, comparing them, even though it's just, there will be an element of, so one suggestion is you use, say, 15 angstrom resolution data to orient 2 completely independent models, and then you look beyond 15 angstroms to see if it's true, if there's anything real there. And a similar thing would be when you're doing model fitting. You've got your 3D model from all your EM data, you think it's nice, and then you've got an X-ray model or an NMR or another EM model from another published bit of work, and you're going to dock it, and you move it in, you fiddle it around, you say, perfect, submit to nature. But it'd be quite good if there was some way of proving that it was true. So one thing you could do again would be calculate a Fourier map from the coordinates, and then use data, let's say, only to 15 angstroms to do the orientation, and again, compare it beyond that. So the idea is to somehow or other remove some data from the comparison so that it never saw the rest of the data. And then you have and the X-ray people do that with the free R factor. So we need a few things like this in the EM field. And I think it's not really established yet as a practice. But Henning, sorry.
Yeah, so I'm not sure if you limit the data set to 15 angstroms, that you can do an unbending in 2D crystals that then gets you to much higher resolution if you don't have that resolution in your reference. And so my question is, if you speak of R3, if one couldn't just, when you select your spot list, if you could have a random subset of 10% of the spots that you explicitly don't use, even though they were there, and then you do your unbending as good as you can, and then you look at the average intensity only from the spots that you did not use, but in all the resolution ranges. And then you do some automatic parameter testing of all the possible parameter settings and look for the one that has the highest R3 value for the unbending intensity. But then still include also the high resolution spots if they were there. So,
yeah, no, you could, if you leave out, if it's 2D crystals you're talking about, and you leave out 10% of the low resolution spots
from the unbending,
you can also look at them, and they will be equally untainted by the orientation.
Yeah, you don't limit the resolution during the unbending.
Yeah, but I don't think you have the problem. I think there isn't any image processing based 2D crystal structure that is under a cloud of suspicion.
Oh no, there are many. I made many of those, yeah. It's very easy. You make a reference that is tiny, and that the unbending parameters go wild, and then you have a 1 angstrom or even better resolution in your negative stain map. With IQ spots up to the Nyquist frequency. It's very easy to do this with 2DX. So you need a small reference and a large quad search range or so. It's very easy. Yeah, so with negative stain data, 1 angstrom, I did that many times. It's very easy, and so I think you need that.
All right, well, that'd be good.
At least when I use.
I should say we had a program called WM box, which was a weighted M by N box. So you fed in the distribution of where in your image the good bits were and where the bad bits were, and you could make it bigger or smaller. And we thought this was improving the data, and we did publish it in one paper. But then later we found people were doing more or less what you said, and they found by making it smaller and smaller and smaller, the index they were looking at, this H thing, got bigger. So we physically destroyed that program because we thought it was too easy to misuse it without knowing you were misusing it. So somehow or other you need to create foolproof procedures so that even a very hard-working but not theoretically based person can't get themselves into trouble, like you were saying. So is there some way of putting a health warning or a blockage on that procedure? That would be useful to do.
Yeah, the other way is to re-unbend an already unbent image. Then you also get it to very high resolution. That's the other pitfall that we have.
But you must have done. Is it because you're? I mean, another common. You put a mask in, and it's the mask you're sharpening. You're creating. But if there's where did that? If you weren't using the high-resolution data to do the unbending, obviously if you use the high-resolution data, it'll just sharpen all the noise, actually. Exactly. So whatever you put into the unbending always gets stronger. So that's why you have to leave something out. But we've chosen to leave out the spots you couldn't see anyway, and then look at them. That's a really good test, because it's actually that's the bit of the structure, the high-resolution bit that you're interested in. So when it appears and you haven't put it in, you know you're doing well. So maybe in negative stain, if you just leave out, I mean, it doesn't need to be 15 angstroms. I was only saying that because in single particle work, once you're at, say, 6 angstroms, you can see helices, 4 angstroms, you can see beta sheets, 3 angstroms, you can see side chains. Then you validate it in another way from the chemistry. But the danger is for blobs that are 6 angstroms, 10 angstroms, 15 angstroms. And so then if you want to leave out the high resolution, you have to decide where is it you're going to leave it into. And I was just saying 15, but you could use 12 or 10. But you know, if it's out near the resolution that you think you're going to get, then of course, you know, this particle has a certain size, these Fourier cutoffs aren't very sharp. So you really need to look fairly far beyond the resolution that you've used in some kind of orientation determination or unbending as well.
But isn't it that one can get, for instance, in optical microscopy, positions quite precisely?
Yeah.
Although you don't have this high resolution, but the position of beads or such signals, that's quite precise.
Yeah.
For the unbending, you only want to know where that unit cell is to a very high precision, even it's only sort of a blob. I mean, you don't really need a very sharp cross-correlation.
That's right.
And therefore, I in a way like your approach, just to use a low resolution and observe what then somehow comes up. Because you, as you just described, you might actually create much more difficulties if you would pick up all the high resolution stuff which is perhaps not that well defined.
Yeah. You know, you're right, in that cross-correlation map where you're looking at the peaks, if the spots that contributed to the cross-correlation map are, shall we say, 7 angstrom resolution, your peak will be 7 angstroms wide or 6 angstroms wide. But you can find the center to within half an angstrom, and that's what allows you to unbend it and get the 3 angstrom resolution things. I think it all hangs together quite well. Similarly with single particles, I mean, you find the position quite accurately and the orientation within a degree or two, or bigger particles find that. So I think it's you know, you get a faith that it is working. Some of them are working, and then some of them you're worried about. It's the ones that you're worried about that somehow that we need more robust validation criteria, actually. Yeah.
For the two-pair validation, if you don't have two pairs, you have just very nice one image of hypothetical particles and they're oriented.
Yeah.
So if you have just one image with a lot of
Particles.
particles oriented to different angles, their projections, can you actually choose from this single image tilted pairs, like one that face the two-fold versus the one that face the three-fold symmetry, and actually make these pairs if you don't have
I don't think so, because I mean, so what we were suggesting is you find the orientation of a particle from an image, and then you take another picture of the same particle from a different direction, and then you ask, can you predict, or can you determine from the first particle, can you prove from the first particle that its orientation is consistent with the view you get of it? And if you don't have the second view, you can't do what we suggested, so you'd have to do something else, like dividing your, you know, into 2 piles. For example, I know that in the hepatitis B virus case, which is the first one that we had experience with in Cambridge, Alistair Stephen and James Conway, they had a 9 angstrom hepatitis B virus structure published at the same time. As Bettina had about 20 micrographs, they had only 1 micrograph. It was a very good micrograph, and it had 1,000 particles in it. And they, you know, they picked them all out, and 60-fold averaging, of course. So 60,000 asymmetric units was 9 angstrom. It was really a nice, but that was quite a big. Actually, we haven't done this tilt pair on hepatitis B. That's about 3 megadaltons also. But you know, no, it is. So our general idea is normally people take, say, 50 micrographs because it's 1 cassette, and then they go home. But the idea is that at the end, you should use your last 3. You should take 3 fields of view, and then take an untilted picture, just like you were taking the other 50 particles, and then you take another one at a different angle. And if it's a big particle, 5 degrees. If it's a little particle, maybe it'd be 30 degrees. So I think we've done some, we thought we better try ribosomes, since so many people in the world seem to work on the ribosome. And it's about 3 megadaltons, but it's got RNA in, so it's got twice the contrast of protein, and RNA is half the radiation sensitivity. So they have a factor of 4 advantage. So our argument is that a 3 megadalton ribosome, 70S E. coli, should be as well oriented as a 10 megadalton protein complex. So we're expecting it to be really rather good, without any orientations in it wrong at all. So we've got some pictures, and this is Laurie Passmore in Cambridge, and it was pictures taken on FEI's Titan about 2 or 3 weeks ago. So, you know, that's going to be one of these things, and that'll say maybe something about ribosomes and RNA, how easy it is to do or how hard it is to do. And I think the more we have, so once there's 20 of these things, there'll be a kind of, let's say, there'll be a sort of backdrop to the field, and hopefully people won't feel comfortable unless they've done a tilt pairs. Anyway, that's the general idea, is to make it easy and to encourage people. And if it works, and people say, well, clearly none of these ways of doing the tilt pairs have worked, therefore my structure is wrong. That would be one conclusion. That's not necessarily true, though, because with the multivariate statistics and the class sums, it's possible that you could go right down into the noise level and get something. So I think what would be nice is if the people who do multivariate statistics and class sums could combine that somehow or other with tilting to validate the class sum somehow or other. And I'm not sure quite how you do that. I think they have this, Rademacher random conical tilt, where you take an untilted view, you classify them, and then you take the tilted view and you get, let's say, 10 or 20 3D models, each one from a different class sum. So in some sense, if you had, you then combine them together, you already have the tilt pairs in the random conical tilt pairs. So if they were to just graft onto the end of that, some kind of test, so some people may already have data that could be tested in this way. Other people would have to recollect it, but next time I think it's just worth putting onto the end of a data collection run 2 or 3 tilt pairs, and then if that data set works out, at least you can try this. You know, you're not obliged to tell anybody that you tried it.
So have you ever tried this with a model that was wrong, like in yours? Or
Yes.
different clusters of angles? Or
No. So there's been various projects at LMB in Cambridge, and as I remember it, 4 of them worked and have been published, and 4 of them that were either ice-embedded or negatively stained. You deal with negatively stained structures as well, actually. It doesn't need to be ice-embedded. And it basically didn't work. There was no minimum, and the reason people were doing it, they didn't have the faith that the thing was anything other than massaged noise. And since it didn't work, it wasn't published. So, you know, it's just basically jumped. So we have had 4 examples, and I can't remember what they were, but there's some of these S-script complexes, but they've been, it was used to reinforce the view that it hadn't worked, that the whole procedure, whatever it was, some combination of various scripts hadn't worked with all. So I think I suppose it's disappointing if it happens, but it's better than finding later on that your reputation is in shreds because you published it wrong, a wrong structure.
What are the most fragile parts in a protein under the rotation dimension?
Can you say again, what are the most?
The most fragile part of a protein. Amino acid.
The most fragile part,
Yeah.
sorry, yeah.
Sorry.
Yeah, it's been worked out largely by people taking 3D crystals that are of very big crystals, and with the new modern synchrotrons and really good detectors like the ones Clemens was talking about, you can collect complete data sets repeatedly, 100 of them, before the crystal is dead. So you can look at things fading. And I think that the general idea is that disulfides and cysteine residues are the first things to go. So the cysteine somehow or other is, it falls off and then diffuses away. And then exposed aspartic acids, asparagines, glutamines and glutamic acids, they then go. And then, so that's 5 residues. And then the last ones to go are phenylalanine, tyrosine and tryptophan, because they have the aromatic ring, which is more resistant. And then in between, you've got 12 other amino acids. They're like leucines, valine, serine, threonine. They're probably in the middle in terms of robustness. And then when you go to DNA and RNA, they've got the very big adenine, cytosine, the rings, and they are more resistant than tryptophan, phenylalanine, and tyrosine. So DNA and RNA tend to be, and they have more contrast because of the phosphates. Although I don't think anybody's looked at radiation hardness in terms of a DNA structure yet. That would be quite an interesting thing to do. But probably, the base stacking will be relatively well preserved. It might be the phosphate sugar backbone that's more sensitive. So I think that's all. There's quite a lot of papers published in the literature actually about that. Well, mainly on lysozyme, which has disulfides and aspartics. In fact, at the active site, you've got an aspartic and a glutamic, which is exposed in the active site. So these are the things that go. And then obviously water molecules, move around and disappear, sodium ions and things, but as a consequence of the protein. And of course, you're only looking at the average of all of them. In a lattice, it might be that one protein molecule has had one residue destroyed, the next one is the next. So you're only looking at the average of 10 to the 9th structures, and you're looking at all 10 to the 10th. So. And it will be the same for electron crystallography and imaging in single particles. Bacteriodopsin didn't have any cysteine or disulfides, so that wasn't obvious. But certainly there were some earlier theories about how so superbly accurate was electron microscopy that you could determine the charge on residues. And that turns out to have been due to the residues falling off due to radiation damage.
Has this been proven?
Pardon?
Has this been proven?
Was it improved?
Has this been proven?
No. But it's certainly wrong. Sorry. Yeah. It's just an opinion. Sorry.
So you have stressed many times the movements during irradiation, both crystals and single particles, and that could be a reason why you have a distribution of the angles. I think for single particle work, heterogeneity is a major issue. And having just a few projections, couldn't that be also a reason why you have a distribution of the projection angles?
Say it again now.
If you have a heterogeneity in your specimen,
yes,
and you are checking the tilt bits.
Yeah. Some of them might be bad because the particle is bad.
Yes.
Yeah.
Has a different conformation or something like that. So.
Yeah. That's possible as well. And then of course in a big icosahedral virus, some of the subunits could be bad, but the rest of it might be okay still. No, I mean you can always say that my resolution is limited, this part of the structure is floppy, and that might be true actually. And in the end, if you've eliminated everything else, that might be. But actually, initially it's more productive, I think, to, in a way, that suggests you've done the best you can and you should stop work. But if it turns out that it's due to a technical thing like, the dose isn't enough or that you've got the defocus wrong, it might be that you can improve it. But I agree with you. In the end, there are floppy structures. For example, I think we're now fairly convinced that pyruvate dehydrogenase, which is designed to be floppy, isn't well ordered at high resolution. There are no X-ray structure crystals. that go beyond about, well, of the icosahedral ones, beyond about 5 or 6 angstrom resolution. And the EM is like that as well. And I think it's true that there are lots of people now working on very big data sets to divide them into subpopulations that are sorted according to some flexibility of some part of it. And that might still be true, but if you can improve the images, then that'll make it either possible to sort them into more subpopulations or have more data in each particle, so that you find out that some of your sorting is due to technical factors. It isn't real. I mean, that's another thing. So in the same way that some structures, you put all the data in, you throw away a little bit of it perhaps, and you're still not sure how right it is. Similarly, as soon as you divide your structure into 5 subpopulations, you have some uncertainty as well as to which parts of those structures are right, and is the difference real, or has it been created by the computational, using the noise to separate them. And again, there are no real sort of rigorous validation tests that you can do. Although I suppose if you had a drug that you could add that would put the population over one way and another drug that would put it the other way, and then you did the same analysis on both and got to the populations, I mean, there might be things like that. But I agree that in the end, floppiness and surface variations that might well be held together in a 2D or 3D crystal might be, in the longer term, once all the technical factors are solved, might be what affects practically what approach you take when you're interested in a particular aspect of the structure.
Any more questions, or can Richard have some beer? Sorry.
Hi. So we actually tested this as well. We were thinking that maybe the particles are radiation sensitive, so we tested it on a negative stained sample, take 2 kilopascals at 30 degrees. We found that 50% of the particles can fall within like 0 to 60 degrees and center at around 28 degrees. The rest, 50% were random. So
that was tilt pairs, was it?
Yes. Then I read your paper, then I got the feeling that if you introduce more and more parameters, you sort of like make yourself fall into a dangerous position. You introduce more and more parameters, you get better and better fitting, and then you claim that you are getting better and right solution. But this is how can you judge that you actually are in this type of situation?
You mean in the answer to Angie's question, what did we do to improve it?
Right.
Well, I mean, we weren't doing anything that you don't do normally. For example, we're determining the defocus. We're using a resolution criteria. We're sharpening the data one way or the other. They're not really new parameters. They're parameters that were already in there.
Yes, but those parameters are going to change the criteria. Say you use the phase voltage difference to judge how well you are doing. And all the parameters introduced well from certain angle change that. And that will lead you to what you expected to see.
Well, no, but however we changed the parameters, we never found a minimum at 8 degrees, 30 degrees, this direction or that direction. It was only along that line, and it was only at 10 degrees. And it was less than 10 degrees, and our interpretation of that is that we reckoned our sample did have some contamination on it, surface contamination. Our microscope was an F30, it contaminates 10 angstroms an hour. You get some snow on it, and when you take a picture, the snow is on one side. You tilt it, you take a picture, you got the same snow near the same particles. And our argument was that in doing the alignment, if you've got a very noisy image and you haven't got the resolution right and so on, you may quite often get orientations that are completely wrong, but they've oriented on some other piece of dirt that was in the same field of view in each case. So therefore, that's why we think that we got a minimum at 1 degree or 7 degrees, or if you just put random numbers in, it's completely flat. So I think the thing is that the procedure and the sharpening and so on, it doesn't know what the goniometer setting was when you took the picture. You wrote that in your notebook, and that is your piece of information. And I don't think, supposing I pretended I'd written down not 10 degrees, but 20 degrees, nothing I could have possibly done could ever have made it, because there was never any hint of that. So, you can also sit down yourself and say, what other criteria could I do? You could take tilt triples, for example, and then you could say, okay, I've got this minimum at plus 10. I'm not entirely convinced, but I took a third picture at minus 10. And of course it'll have higher radiation damage. So, there's a lot of variations you could do on this theme if you were still unconvinced about it. And I'm not arguing that this is the only thing that you can do. It's just one thing that we happen to come across that we think is a validation criteria. And actually, the other thing I should say, which I haven't mentioned so far, is the protein data bank will accept your structures determined by electron pi microscopy into the EM data bank. And they have apparently become quite worried that people are depositing a lot of crap in their data bank. And so in about 6 or 8 weeks, there's supposed to be a meeting that some of the people here are supposed to go to at Rutgers, at PDB, to discuss two things. What should the protein data bank EM density map deposition people ask the people who wish to deposit their structure to deposit before they accept it? And then sort of hidden in the background is not formally stated, is what should referees of papers, in the same way that X-ray people ask for free R factors now, what should they say they would like to see in order to judge whether they believe that it's true or not? So apparently there's two groups. One is supposed to do maps. So if you created a map, what should you have done to show that it's correct rather than incorrect? And usually in scientific papers, actually, you do a piece of work, and the data in the paper proves the conclusion that is announced in the abstract. And I think one of the troubles with some single particle work, not all of it, but some of it, is you've got a self-consistent map, and you don't really know. You have to take it on faith. And actually, I've refereed quite a lot of papers. I said, well, I'm not entirely convinced by this, but there's nothing that's stated that shows that it's wrong, and therefore probably it has to be published. And I've said this before actually, but the classical one was the IP3 receptor. Maybe there are some people here who weren't on that, but there were 4 papers published. They all got through the refereeing, they were all fine, but when you look at the 4 structures, there is no resemblance.